The term biomass refers to all sorts of living matter, whether natural, grown and bred, as well as their residues. Biomass is essential to human beings. For thousands of years, people have used biomass as a source of energy. In the 20th century, oil has made life easier. But the negative side is that nature, or the environment, is seriously affected. Would the solution today consist in reverting back to basic energies, such as the sun and biomass? And if we do this, what would the cost be? Recent technologies can convert biomass into hydrocarbon within a few hours. The willingness to change is therefore mainly a matter of commitment. To what extent can biomass replace fossil fuels? What are the benefits for the environment, for society, for climate change? In 1 year, humankind consumes the equivalent of 12 billion tons of oil. In 1 year, the solar energy received by the Earth is equivalent to 90,000 billion tons of oil, and the energy stored in biomass growth amounts to 72 billion tons. All the energy needs of humankind in a year could be met by collecting an hour of sunlight, or 1/6 of the biomass production. Yet renewable energies only account for 13% of the global energy package, which is dominated by non-renewable energies: oil, coal, gas, and nuclear power. Biomass is number 1, far ahead of hydropower, wind, solar energy, geothermal, and tidal power together. Biomass, which is at the beginning of the food chain, is also at the beginning of the energy chain. Photosynthesis is a biological process that enables plants to synthesize their own organic matter from atmospheric carbon dioxide, CO2, and water. Photosynthesis mainly produces sugars. For example, 6 CO2 molecules and 6 water molecules are needed to produce 1 molecule of glucose. The reaction also produces 6 molecules of oxygen. CO2, mainly responsible for the greenhouse effect, is thus trapped in solid form within the organic matter. The energy potential contained in organic matter is higher than that of the initial products, CO2 and water. The plant captures the energy necessary from light. This energy is stored in the form of binding energy between atoms. The return of biomass to its initial components releases this energy. It is this energy that we recover when we eat the plant or when we burn it. But like all other living creatures, plants breathe. This respiration results in the opposite of what photosynthesis produces. The plant consumes oxygen and sugars, yet produces carbon dioxide and water. During the day, photosynthesis compensates for the loss in organic matter due to breathing. Growth only occurs if the amount of organic matter produced by photosynthesis exceeds the amount needed for breathing. At night, only breathing takes place. Lastly, plant decay in the open air obeys the same law as that of breathing. Now, let's have a look at the life cycle of a tree. The young tree stores more and more carbon. As it grows older, its breathing catches up with its synthesis of organic matter. Consequently, carbon storage declines. The tree dies. As it decomposes, it releases all the carbon it will have stored in its lifetime. It is therefore a carbon sink and a source of carbon. Over its whole life, the net result is zero. The tree has stored or produced no carbon, and it has not stored or produced oxygen either. In order to limit the greenhouse effect by stocking a maximum amount of carbon, there is thus an optimum age at when the tree should be cut down and replaced with a sapling. If the tree is burned instead of being allowed to decay, we find the same result, but the reaction is faster. If this decay takes place in the absence of oxygen, for instance in a rainforest swamp, the tree will produce methane. Methane is a much more powerful greenhouse gas than CO2. So in its whole life cycle, the impact of this tree will have been negative because it has produced greenhouse gases. By playing a part in natural systems, humankind can therefore control the reabsorption of atmospheric CO2 and limit the emission of greenhouse gases. For Elizabeth Linette, fuel wood is a traditional resource in France that could account for 40% of the national harvest. Yet it is missing from official data because it is gathered by individuals and is thus not included in official statistics. On a global scale, the carbon flow stocked by biomass is about 62 billion tons a year. This carbon is considered as circulating because a major part of it goes back into the atmosphere due to the decay of biomass. Photosynthesis is the driving force of this carbon cycle. Related to this main cycle, there are other lesser ones. Atmospheric carbon is on a balance with the carbon dissolved in water. Part of this dissolved carbon sediments, while sedimentary limestone is burned by volcanoes and returns to the atmosphere. Finally, a tiny fraction of biomass will be gradually fossilized, but it will require millions of years for this biomass to be turned into coal, oil, and natural gas. From the industrial era onwards in the 1850s, human beings began to draw from fossil fuels. The burning of these resources provoked additional CO2 emission into the atmosphere. Deforestation and the use of limestone, for example for the manufacturing of cement, also generate CO2 emission into the atmosphere. Humankind thus releases a new source of CO2 called anthropogenic CO2. This flow of carbon released into the atmosphere brings about an imbalance because it is too large to be absorbed by natural phenomena. Thus, the concentration of atmospheric carbon that had been stable for years has been increasing since the first industrial revolution. This has increased and continues to increase the greenhouse effect. By capturing and releasing CO2, the plant creates a flow of carbon. The whole biomass is a stock of carbon. The flow and the stock are related. On Earth, the carbon stock is divided between 4 reservoirs. The atmosphere, 750 billion tons of carbon, mainly in the form of carbon dioxide. The biosphere, which represents the organic carbon of biomass, 1/4 of it is alive, and 3/4 is dead or decaying. The hydrosphere, water, contains dissolved carbon. The lithosphere, the underground rocks, contains most of the carbon as a mineral. There are rocks of organic origin, coal, oil, and natural gas, called fossil fuels, all created by the fossilization of the biomass. There are also limestone rocks, formed by the sedimentation of shells and the precipitation of dissolved carbon. The amount of carbon that can still be released into the atmosphere is enormous. Populations are not equal with respect to their energy consumption. There are large consumers. They consume 10 times more than small consumers. And there are average consumers. Of course, the larger consumers could consume less, but they are very few. In fact, areas where energy consumption per person is the lowest are the most populated, have the strongest population growth, have the highest increase in energy consumption. But these consumers consume so little that it is difficult to ask them to consume less. So even with a balanced consumption of around 2.5 tons of oil per person per year, more energy will have to be produced, all the more so as the world population keeps increasing. In order to achieve sustainable energy consumption, energy production should not resort to using energy stocks, but to using energy flows. We should no longer draw on fossil fuels or trees, but capture rather solar energy, wind energy, or the flow of biomass production instead. We must use energies that are able to be renewed as fast as we consume them, that is, renewable energies. The use of biomass consists in diverting part of the cyclic carbon towards human activity. Once consumed, this carbon returns to the cycle it would have had if humans had not intervened. That is to say, there is no further emission into the atmosphere. On the contrary, what is taken from the biomass saves fossil fuels and accordingly reduces emission into the atmosphere. But biomass production, transformation, and transportation have an energy cost. The economy in greenhouse gas should then be calculated over the entire cycle. Shortened circuits that already exist in the food economy also have a part to play in energy production. The following experiment started in the town of Villeneuve in France in 2005. Vegetable oil has already enabled them to travel 2 million kilometers. It is produced around the town of Villeneuve. Direct sowing cultivation saves plowing as well as the use of fertilizer. In 1900, Rudolf Diesel devised his engine to work with vegetable oil. He thought he would revolutionize agriculture because he would make farmers self-sufficient on energy, and they would even become energy producers. Before 2008, easily transformable substrates were used, often foodstuff, sugar and vegetable oil, in order to obtain ethanol and methyl esters. These were the first-generation biofuels. In 2008, the food shortage broke out. It emphasized the awareness that non-food biomass should be used to produce biofuels. These were the second-generation biofuel. The second-generation biofuels used lignocellulose as a raw material. Lignocellulose is the main component of plants. Its transformation thus enables us to use entire plants rather than storage organs alone. The nature of the energy produced depends on the use we want to make of it. We distinguish static use from mobile use. Static use energy is consumed in a fixed place. Mobile use energy is employed to move vehicles. Only a quarter of the energy is used for mobile use, but it is the most problematic energy because it has to be carried within the vehicle. The main constraint is to go far with a low volume of fuel. A lot of renewable energy is produced in the form of heat and electricity. It is difficult to store heat and electricity. Therefore, they are mainly used for static use. The characteristic of biomass is that it is available in a material form, which gives it the advantage of being easily stored. Among the energies that can be easily stored, thus offering the strongest energy content, what we call calorific value, are preferable. The higher the calorific value is, the further we can go. Biomass, wood, has a low calorific value, 16 megajoules per kilo. Besides, the solid form of wood is ill-adapted to power an engine. Gases are used as mobile use energy, methane and hydrogen. They have a very high energy content. But the storage of these gases is still cumbersome and eventually limits vehicle autonomy. Yet hydrogen would be an ideal fuel because its combustion does not release CO2. Enriched uranium has a calorific value of about 500,000 megajoules per kilo. A kilogram of uranium would allow a car to run 200,000 kilometers, but in civilian life, the best adapted energy for mobility is thus in a liquid form. It is then called fuel and biofuel when the resource is biosourced and not a fossil fuel. Liquid biofuels are already part of everyday life. Ethanol is mixed with petrol. Pure vegetable oil is also used. But petrol and diesel, with a calorific value of 43 megajoules per kilo, surpasses all liquid fuels. The fuels with the highest calorific value contain the least oxidized molecules, i.e., those with the lowest proportions of oxygen. Petrol and diesel do not contain oxygen atoms, but only hydrogen and carbon atoms. They are hydrocarbons. Nowadays, transport uses half of the crude oil produced. The reason for this is that it contains hydrocarbon molecules which do not explode, and it has a high calorific value. Therefore, what is at stake here is to produce a new generation of liquid hydrocarbons from biomass instead. It has taken nature millions of years to produce hydrocarbons. Are we able to do that successfully in a few hours? The raw material for second-generation biofuels, lignocellulose, is a complex entanglement of macromolecules. Thousands of glucose molecules are bound together in linear chains to form a molecule of cellulose. Cellulose forms cable-like filaments known as fibrils. Lignin is like a corset that stiffens the cellulose network and brings solidity and impermeability to vegetable cells. Hemicellulose binds cellulose molecules and lignin. This structure makes biomass highly resistant. This is the difficulty with second-generation biofuels. How can we deconstruct lignocellulose to obtain simple molecules that could be used by traditional chemistry? The stakes are of the utmost importance. In the first-generation processes, simple cold pressing would enable us to extract sugar or oil. The second-generation processes are far more complicated. We distinguish microbial methods from thermal methods. After chemical treatment, the microbial methods use enzymes which selectively split up macromolecules into simple sugars. Among other things, we can collect the glucose molecules from the cellulose. The thermal methods, which are more drastic, pulverize all the lignocellulose macromolecules into simple molecules, hydrogen and carbon monoxide. In order to meet energy needs, we can thus choose between several biomass resources. There are products of agriculture, seeds, which produce starch or sugar, and oil-producing seeds. These resources enabled us to develop first-generation biofuels. Nowadays, technologies have improved and allow us to use the byproducts of agriculture as well as the products and byproducts of forestry. This resource, rich in lignocellulose, led to the second-generation biofuels. The cultivation of microalgae has led to third-generation biofuels. Microalgae produces sugars and oils with yields per hectare that could be 10 times as high as those of land crops. These techniques are quite recent, and their industrialization is still in progress. Lastly, there is the issue of waste. Wet waste can be methanized to obtain biogas and provide gas, heat, and electricity for the energy networks. Dry residues, in the form of lignocellulose, enable us to produce biofuels. Burning wood allows us to proceed directly from the energy resource to the energy use, heat. But generally, a transformation process is needed to convert the resource into a specific energy use. It is in the biorefineries that this transformation takes place. If we consider mobile use, the most favorable solution of the moment are found in second-generation biofuels. We estimate that, compared to fossil fuels, first-generation biofuels reduce greenhouse gases by 30%. Second-generation biofuels reduce them by between 70 to 90%. This reduced impact is because these resources already exist. Often, all we have to do is harvest them. But to launch an industry, raw materials must not only be available in sufficient quantity, but must also be sustainable. Is this the case? Around the globe, land areas represent 14.9 billion hectares. 10% of this surface is occupied by farmland, 23% is pasture, 26% is forest. Everything else is desert or built-up areas. This means that biomass covers about 60% of the land. Yet plants don't grow everywhere at the same speed. We can access these differences by measuring the net primary production. It is the mass of organic matter synthesized per square meter and per year. On land, organic matter develops 5 times faster in tropical areas than in temperate areas. The net primary production varies according to a series of factors, including light intensity, water, temperature, and the concentration of CO2. We could almost say that thanks to the CO2 released by humankind, plants grow faster. Let's take the example of forests. They produce per hectare and per year 2 cubic meters in the far north, from 5 to 20 cubic meters in temperate and dry tropical areas, from 50 to 100 cubic meters in wet tropical areas. Currently, the average rate of wood harvesting is 1 cubic meter per hectare per year. Let's imagine that we took 2 cubic meters instead of 1 cubic meter. This alone would correspond to 8% of humankind's energy consumption. In particular, unused wood debris left to rot in forests already represents 60% of the available biomass. In the countries where forests are managed, they are expanding without fertilizer and without irrigation. Processes that are being industrialized now enable us to convert biomass into hydrocarbons. Biomass that already covers 10% of the world energy consumption could provide 25% of that. By resorting to renewable energies, a lot of countries could improve their energy autonomy. The same is true for food autonomy. Solutions have to be found. Researchers are working on them. But it is a global social project that must be set in motion. We have to reconcile the natural advantages offered by the soil, climate, and the location with biodiversity and employment. This is necessary to provide humankind with sustainable sources of food, material, and energy.